Welcome to our Quantum Deep Dive. Today, we're exploring a hidden connection right at the heart of modern physics, and it's all based on the fantastic work of author Georg Owe Schnippet.
So, what you're looking at is an absolute marvel of 21st century engineering. It's the core of a quantum processor, a machine with the potential to solve problems that are just impossible for even the most powerful supercomputers. We're talking revolutions in medicine, materials science, AI, you name it. But here's the twist. The fundamental principle that makes this futuristic device actually work, it wasn't discovered in some modern Silicon Valley lab. No. Its origins are in a low-temperature physics laboratory in Berlin, Germany, all the way back in 1933, a time of massive political and scientific upheaval. So, how in the world are these two things connected? A cutting-edge quantum chip and a nearly century-old experiment. What's the invisible thread that links them across time? Well, to understand that, we need to trace the story of a very quiet discovery that ended up changing everything. Our journey today is going to start with the incredible promise of modern quantum tech. Then we'll travel back to a mystery that puzzled physicists for decades, witness the elegant experiment that finally cracked it, and see how that one discovery echoes directly into the quantum computers of our future. We'll even meet the quiet researcher behind it all. Okay, let's dive right in. Our story begins not in the past, but right now, with a whole suite of technologies that are already starting to reshape our world. From quantum processors like Google's Sycamore to massive particle accelerators like the Large Hadron Collider, they all rely on a very special state of matter. And it's the same for things like squids. These are the most sensitive magnetic field detectors ever created. They can literally map the tiny fields produced by the human brain. All these incredible tools share one common secret ingredient. To find that secret ingredient, we have to rewind the clock back to the early 20th century. Physics was in the middle of a total revolution. You had Einstein's relativity and the new quantum mechanics just turning classical physics completely on its head. And in the world of labs and experiments, a new mystery was brewing. So back in 1911, a Dutch physicist, Heike Kamerlingh-Onnes, discovered something really strange. When you cool mercury down to just a few degrees above absolute zero, its electrical resistance completely vanishes. Just gone. He called it superconductivity. For the next 2 decades, scientists knew this weird state existed, but a huge piece of the puzzle was missing. And that missing piece was this one central question. Look, everyone knew that electricity and magnetism were linked. So what happened to a magnetic field when you put a superconductor inside it? Did the field get trapped? Did it pass right through? Honestly, nobody knew for sure, and the early experiments were just confusing and contradictory. The definitive answer to this puzzle finally came in 1933 from an experiment at the Physikalische Technische Reichsanstalt in Berlin. This was one of Germany's leading institutes for fundamental research at the time. The experiment was carried out by what turned out to be a perfect partnership. You had Walther Meissner, the experienced lab director, a real leader in the field. And then you had a Robert Ochsenfeld, his collaborator, a researcher known for his uncompromising accuracy and a patient, methodical approach to his work. Their experiment was just beautifully simple. They took a cylinder of tin, placed it inside a magnetic field, and then cooled it down past its critical temperature. That's the point where it becomes a superconductor. As it crossed that threshold, sensitive coils were measuring the magnetic field inside, and the result was completely unexpected. The magnetic field wasn't trapped or frozen in place. It was actively and completely pushed out. Now, this result was revolutionary. I know it might sound like a technical detail, but this discovery revealed that a superconductor wasn't just a perfect conductor. It was something else entirely, a fundamentally new state of matter that played by its own unique rules. And this right here is the crucial difference. See, physicists had this theory for a hypothetical perfect conductor, and it predicted that it would simply trap any existing magnetic field inside when it got cold. But that's not what Meissner and Ochsenfeld saw. They found something different. It didn't matter if the field was there before or after cooling. The moment the material became a superconductor, it actively expelled the magnetic field, kicked it right out. Their 1933 publication boiled this whole discovery down to the simple, powerful statement you see here. B equals 0 im Innern des Superleiter, which just means the magnetic field, B, is 0 inside a superconductor. This wasn't just an observation, it was a defining law for this new state of matter.
This phenomenon was named the Meissner-Ochsenfeld effect, and honestly, its importance cannot be overstated. It was the first experimental proof that superconductivity wasn't just about zero resistance, it was a macroscopic quantum phenomenon, a collective quantum state that was big enough to see and measure with lab equipment. The strange rules of the quantum world were showing up on a scale you could hold in your hand. So how does that fundamental piece of knowledge from a lab in Berlin in 1933 become the engine for the most advanced technology of the 21st century?
Well, that perfect magnetic expulsion isn't just a cool fact. It's the core operational principle for today's advanced tech. The Josephson junctions that act as quantum switches, the super powerful magnets and particle accelerators, and, most importantly, the superconducting qubits at the very heart of quantum computers, none of them could exist without it.
And here's why this matters so much. A quantum bit, or a qubit, is incredibly fragile. Its delicate quantum state can be destroyed by the tiniest stray magnetic field. The Meissner-Ochsenfeld effect provides the ultimate shield. It lets engineers create a magnetically silent environment where a qubit can do its thing, totally protected from the noisy outside world. The effect is named after two men, of course, but the story of Robert Ochsenfeld in particular offers a really powerful lesson about how discovery actually happens. Accounts from his colleagues paint a pretty clear picture of Robert Ochsenfeld. He was described as a researcher who was defined by an uncompromising accuracy and methodical rigor. A quiet, self-effacing guy who avoided the public spotlight, much preferring the focused work of the laboratory to the lecture hall. And he was known for his cooperative spirit, this belief that true scientific progress came from a shared effort, built on mutual respect and the free exchange of ideas. You know, when we put it all together, Ochsenfeld's story and his discovery leave us with a powerful message about the nature of science itself. When they walked into their lab in 1933, they weren't trying to invent the building block of a future computer. I mean, they couldn't have possibly imagined such a thing. They were driven by pure curiosity, just a desire to solve a fundamental puzzle about how the universe works. And this brings us to a final provocative thought. The story of the Meissner-Ochsenfeld effect is this powerful reminder that the world-changing technologies of tomorrow are being built on the foundations of quiet, careful, curiosity-driven research happening today. Which really makes you wonder, what secret is being uncovered in a lab right now that's going to define the 22nd century? We'd like to once again thank Jörg Ove Schneppat for the incredible research and writing that made this deep dive into scientific history possible. Thank you for joining us. For more on this fascinating topic, you can visit schneppat.de. Goodbye.
Schneppat.de is a private project by Jörg Ove Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.